In physics scholarship, there are some questions that ask you to derive or show a formula. At first glance, these questions may seem unholy, like, what even is this? But don't worry, I will show you a trick I used to apply and it would work 90% of the time.
But what about the other 10%?
It's called reverse engineering. Reverse engineering is a process or method through which one attempts to understand through deductive reasoning how a previously made device, process, system, or piece of software accomplishes a task with very little, if any, insight into exactly how it does so. Blah 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 blah. According to my rough estimate, the number of questions with reverse engineerable formulae in recent years would fluctuate between 2 to 5. Basically, it's a backward mindset. Normally when you solve a question like this, you would work from the problem until you get the answer that aligns with the given formula. But what if I told you that you can work backward using the formula given to then work out how you can get the formula? It's a bit confusing, but anyway, let's get to one example. This is one example from 2019. The question is, a mass M connected to an inextensible light rope of length L is allowed to swing down from a horizontal position to the vertical as shown in the diagram. Show that the maximum tension in the rope is 3 mg. So the conventional way to solve this problem is to analyze the system. If you take into consideration all the forces, which is just level 3 vertical rotational motion, then you get something like this, with gravity, tension, and centripetal force. Now, since the centripetal force is supplied by gravity and tension, we have Fc equals T minus Fg. Therefore, T equals Fc plus Fg. And by plugging in the formula, you have T equals mv squared over r plus mg. Now, we need to do a bit of manipulation here. Note that during the fall, all gravitational potential energy is transferred to kinetic energy as the block goes from its highest state at a standstill to its lowest state. We can then apply conservation of energy, which is mgh equals 1/2 mv squared, therefore mv squared equals 2 mgh. So plugging this into the initial equation, we get T equals 2 mgh over r plus mg. But note that h and r are exactly the same. Therefore, we have T equals 2 mg plus mg, which is 3 mg. Ta-da! Okay, but what about the reverse engineering way? Let's take a look. The question gives you the information that T equals 3 mg in the first place. Well, the first question I would have is where the number 3 came from. Because normally when a block is stationary, then the tension would be exactly 1 mg, which is from Newton's second law. So the number 3 seems weird to just pop out of nowhere. With that in mind, what can you do to sort of manipulate this? Either do some algebraic manipulation, like plus minusing a term, squaring two sides, etc, or do something really basic. What I would do is then intuitively split it into T equals mg plus 2 mg. So now, the number 2 is still there, but at least it's not as counterintuitive as having a number 3 out of nowhere. Some of you at this stage will see that the 2 mg can come from the conservation of energy, but keep in mind that in exam conditions you may not come up with that idea and just completely forget about it, which is the entire reason why I would apply this method in the first place. So what can you do? Well, think, what formula or equation could I have used to get that 2? Well, as you look through the resource sheet, you will eventually find that linear kinetic energy has a 1/2, at which point you should use it as a hint to then continue solving by applying the conservation of energy like usual. So, the correlation here is between the 1/2 and the 2, which acts as a hint for me to come up with conserving gravitational potential energy and EK. Okay, but this example is relatively easy and probably doesn't need the reverse engineering method. But let's say the next part of the question. The rope is replaced by a piece of extensible rubber, spring constant K of the same length, L. Show that the maximum tension reached in the rubber when the mass is allowed to swing down is given by T max equals 3 mg times L plus x over L plus 2x. Like, what even is this gibberish? Let's try to reverse engineering this thing again. First, to dissect the equation, we can see the number 3, which once again is appearing out of nowhere. Secondly, we can see the L plus x and L plus 2x. But if you notice, the L plus x is the same as the length of the rope when it's stretching out maximally, so it makes sense to have an L plus x there. But what about the L plus 2x? It doesn't make sense to have a length that is itself plus 2 times the extension. So, my intuition says that you have to split it into 2 parts, L plus x and then plus x. And same goes with the 3. And if you play around with the equation a bit, you would eventually get something like this. And at this point, when you're stuck again, try to relate any correlation to equations which could have shown up in the question before. And in this case, what acts as a huge hint for me is this equation. T equals mv squared over r plus mg. Or, mb squared over r equals t minus mg. And if you notice, in fact, the term mg times l plus x can be moved to the left-hand side, so that you get t times l plus x minus mg times l plus x. So that surprise, surprise, you can plug in t minus mg for having the same term. So now you're left with this. But also note that l plus x and r are exactly the same, so you can cancel them out. And now you're left with this. Now ask yourself this: what does this equation look like? To me, it very much looks like an equation of conservation of energy. Because there's the mv squared, which is close to 1/2 mv squared, which is kinetic energy, and then the mg times l plus x, which looks like gravitational potential energy. But what about the tx? Now that you know it is conservation of energy, what would the tx represent? Given that the problem is about spring and also there's just an x for extension alone, I would be very confident that the tx must stand for elastic potential energy. But it doesn't look like the typical formula 1/2 kx squared. So, what if they are actually equal to each other? We can indeed see if this is true or not. Just by putting 1/2 tx equals 1/2 kx squared, we get t equals kx. And as it turns out, this is indeed true, because it's the same as F equals kx, or restoring force of a spring. So now, after you have untangled the mess, you can basically work your way up again. And there you go. Once again, keep in mind that although the reverse engineering way looks very random, it's actually really useful if you don't know where to start to prove the equation. In fact, if you read the answer scheme, the first 3 lines are probably the most tricky. Let's say if you didn't know to use t equals kx, perhaps because of pressure or simply forgetting that piece of information, then you wouldn't have sufficient information to piece them together in the first place. Also, another thing to note is that this method is not exactly foolproof. You still need adequate ability to link equations together and have sufficient physics and algebra knowledge. The most important thing, however, is to be as flexible as possible. The moment you get stuck somewhere, just don't be too stubborn, but rather try to link back to the question before that, or the formula sheet, or use a different method. Stay flexy.